Welcome. My name is Alejandro. I work as a researcher in the language evolution team for Kotlin at JetBrains. But today, I don't really want to talk to you about anything related to this work. This is going to be an introductory talk focused on life cycles, coroutine, scopes, and how all these different concepts intertwine together. So that's the main goal here, to understand how life cycles, and we'll talk about what life cycles are, relate to scopes, and in particular to CoroutineScope, which are maybe the kind of scopes we use more often when creating applications in Kotlin. And we are going to do so by looking at examples from different libraries, both front-end and back-end. In particular, today I'm going to start by giving you a brief summary of the main concepts you need to know about structured concurrency to understand this talk, and then we'll look at examples from Compose, also examples from the other side, from Ktor, and then at the end, I'll briefly mention that the idea of scope is not only for coroutines, it also works for other kinds of concepts like resource management, like distributed transaction, but it's going to be at the very end. So let's begin with this summary of what structured concurrency is. This is the underlying philosophy, the way the Kotlin X coroutines library is architected. And the main idea there is that instead of having just jobs here and there, jobs are created and tied to a parent scope. And that help us dealing with exceptions and cancellation. And the main benefit of having this parent-child relationship between tasks, between different things that are running maybe concurrently, is that we turn concurrency, which is often thought of previously as, well, we just create threads and you have to take care of manually, well, keeping track of those threads and maybe canceling those when something goes bad or you need to cancel the entire thing. This becomes now a local concern. So this extra piece of data, the parent-child relationship, actually allows us to have a much more simple model to understand and reason about what's happening with our concurrent code. The second benefit is that we actually separate the logical idea of the task we want to execute concurrently from the actual way of running the task. And I will just talk about this at the very end of the talk, but the idea here is that, well, you have all the things you want to do, and then there is a separate dispatcher which decides, well, I'm going to do one after the other, kind of sequentially dispatching things, or I'm going to have at most 10 things running concurrently. And you actually can see this as two separate things, right? So one is what task you want to do. The other thing is how you're running this. And a side effect of this, that we can actually provide, well, the library can actually provide a more lightweight way to run this task that full threads. We don't need to actually create threads for everything. We can share some of those because we know this logical way of dealing with stuff. So focusing a bit more on the actual Kotlin X coroutines library, what we see is that we have different ways to create jobs. So we always have a CoroutineScope, which is the place which is going to be the parent of all of this. And then we can start a new computation using launch. And this is just thought for computation which are kind of fire and forget. And then we also have async, which creates another kind of block in which we can actually provide a result. And when we want to get this result, we need to await for it, which means that we are actually going to stop at that point if we don't have the result yet, or if we already have it, well, we're just going to get it. And then there is a little operation with similar libraries. The main thing you need to remember here is that the CoroutineScope blocks only completes once every job has been completed. That means that if I launch a job, even though this is not giving me any result, I can await. The whole CoroutineScope is going to wait until the completion of this task to actually be marked as complete and keep doing stuff. So this is a very important thing. We will see later how this especially can affect uh, when for example, in Ktor, a particular request uh, is marked as being finished. Now, this small piece of code with CoroutineScope, async, and launch can be represented. We can represent the parent-child hierarchy of the jobs in this way. So we have the root job, and then we have one async computation, which is safe in database, and we could imagine that inside of it we actually have other child tasks like commit, and in the other side we have save in cache, which is something we're gonna well, just uh, do also concurrently. And then this has some computation inside, like put key and update in memory. And of course, you can say, okay, you've been telling a lot about, well, how this coroutine scopes means that we have parent-child relationship. But why is this important at all? Well, let's see a couple of scenarios in which this becomes quite important. The first one is cancellation. Imagine that we want to cancel all these tasks because, well, let's imagine that this is inside an Android application. We'll look at it briefly, and then this activity it's clear, needs to disappear. So we want to cancel everything which was going on in the background, right? With this parent-child relationship, it's very easy because, well, we just tell the root job, please cancel. And then this root job can tell to the children, well, please cancel. And then this goes down. So you can see that we can just propagate this cancellation request. If we have exception and we have problem, this also helps us. So with the default handling, imagine that we have a problem in committing to the database. Then this will talk to its parent and say, hey, I have a problem. So, you should do something about this. And then the saving database can say, I don't know, but I will just tell my parent. And then the root job can do something, but more importantly, because it knows that there are other jobs running, and because the saving database has failed, what we do in the default case is just to cancel the rest, because what's the point of actually waiting for other work to be done if we know that the problem has arose somewhere else? So everything there will be canceled. And at the end, well, this final problem is going to be given back to the callee of this method. Now, of course, this is not the full story. First of all, there are other policies for exceptions. So we can have things like supervisor, which allow you to actually have a little more control about what you do when something fails. There is something called Coroutine exception handler, which is the way you can define like a more global cooked exception. And there is also another part I haven't talked about at all, which is that you can mark part of your code as non-cancellable. That's important, for example, when you need to dispose of a resource regardless of what's happened, right? I want to run this. You cannot cancel me where I'm disposing of this resource. And the other thing I haven't touched is that all this business is actually cooperative. So sometimes if you want to write very good code, or you are running something which really goes into the inner workings of coroutines, you need to do some explicit. You need to say, oh, at this point, am I sure I haven't been canceled? Oh, if I'm being canceled, do something different. So this has to be explicit. But in most cases, for all the purposes of quite usual applications, you don't actually need to care about this. Good. So before we move on to the examples, one thing you might be wondering is, well, how is this parent-child relationship actually established in the code? And that's where the notion of receiver, something which seems to be completely separate from all this coroutine business, enters the game, and and gives a quite elegant solution to this problem. So the idea here is that you can see we have the function CoroutineScope, and this will take a block. So usually we write this as a training lambda. So we open the brace, then we write something inside. But you can see there that this actually includes a CoroutineScope as an implicit receiver. So it's now kind of in the context of a CoroutineScope. But the launch does something more interesting because there are two CoroutineScope dot in that signature. So the outermost actually represents the parent. So that's the place where the new task is going to live. But inside the blocks, inside the inner lambda, we are going to have a different coroutine scope, and this is going to represent the child task. So let's maybe look at more clear with some actual code. So here we have some coroutine scope, and inside we have launch, and inside we launch, right? Uh, so if we now make explicit what these receivers are, and I'm doing this kind of doing a bit how IntelliJ would do this, but with a bit of color, then we can actually rewrite and see that there are different this. So there are actually 3 different coroutine scopes, and when I call launch the first time and the second time, I'm actually doing this in different coroutine scopes. So we can see it a bit like this. So we have the coroutine scope, and then inside of this, we do the first launch. You see there with the purple arrow, with the purple this. And now when we are inside another launch, then we have a different coroutine scope, and then inside of it, I run something else, which are the green arrows there. So this is going to be key. This idea that the coroutine scopes, which are the receiver, somehow tell us where the parent and the children are going to be related is going to be quite important later on. So this is a very important concept to understand all of this. Good. So we've talked we have summarized what coroutine scopes are. And now let's move to the concrete example. So when we want to see how life cycles relate to these scopes. So to be clear here, I'm taking kind of a very generic idea of life cycles, right? So this idea that some elements, some components of your software usually go through different phases, different stages, right? So the main ones, if you have some kind of resource, are, well, you create it, you operate with it, and then you dispose. And in many of these frameworks, you can do is essentially to hook into this event, to hook into this change of phases and do something at those points, right? So we will refer to these are some stages and there are some transition of the life cycle. So how do life cycles relate to structured concurrency? That's kind of the question we want to answer here. So let's look at the first example, which is going to be Compose. So the Jetpack Compose multi-platform, whatever you want, that's a toolkit to build user interfaces using a declarative approach that was originally from Android, but if you haven't heard about it, now it's expanded to multi-platform. And this is a very simple example in which I'm just creating an application, and this application has some text which says hello Kotlin conf, and then I'm gonna have a button which I can click, and every time I click, I will essentially increment a counter, and the text of the button will change. So you've clicked 3 times. You can see there are like 3 main things. So there is an underlying state, which is this clicks variable, and we use mutable state of to create this kind of place to save this information. Then we can also access the state, and because we are using property delegation, which you can see because we are using there by, then we can access just as a regular variable, and it will actually go and kind of bring it from the storage of the mutable variable. And we can also operate over the state. You see I'm here using clicks plus plus to increment this every time I click. And the whole idea of Compose is that when I do click plus plus, there will be a change on the thing I'm storing, and this will kind of start a new recomposition of the whole thing. So I will have now a new screen, which, let's say we start with 0. Now we clicks goes to 1. So there is a new recomposition in which we will have you click 1 time. However, I can see kind of everybody who has done a bit of Compose, screaming, saying, "Well, what's going on here?" Because you shouldn't be doing this, right? You should be separating your kind of UI from the keeping of the state. And to do so, we often use what it's called a view model. What you can see there is in the view model, we have an underlying states, that's the underscore clicks, which we save this. And then what we often do is instead of just giving free access to this underlying state, we provide a read-only view. Here we have the variable clicks. You can see that it is a read-only thing. I'm using a val there, and then we give specific operations to do this. In this case, the only one which we want is increment, but you can imagine in more complex states, actually, there is like more of a difference between what the underlying state is and actually the operation we have there. Even though here, instead of an integer, we can change at will. We only allow to increment it. Anyway, then inside my composable, we have the view model, and you can see there, then the change to the state now becomes, calling a function there, model.increment, which will then operation, and then reading the state is done through this read-only view of my view model. If you read the compose doc, what you will see is that the view model is actually the one which should be talking to the data layer. We should actually be bringing the information and then kind of keep the UI part to just look at this read-only view, but not really change anything there, which means that essentially the view model is going to be the one interact with the outside world, with in practice being that it's going to be the one where we want to actually have this stash, when we want to maybe have a concurrent thing, right? Because we might download something from the internet, looking at the database, talking to some server. So it makes sense that in the view model is where we are actually going to launch or an async jobs. So what the compose people have done is actually that every view model comes with an associated view model scope, which is tied to its life cycle. So imagine here I'm having a different application, and in this application, what I want to do is access this Open Meteo service in which I can get the forecast for Copenhagen for today, right? So I'm creating this new task, but you can see that I'm launching it, and where I'm launching it is inside the view model scope. So the parent of this task now is going to be the view model scope, and sometimes this is actually a bit hard thing, because we usually think of launch as this kind of top level thing, but it's actually part of your CoroutineScope. So it makes sense that we can provide an explicit receiver, in this case, the view model scope, to establish the context, to establish the parent for this particular task. And remember, this already means that if the view model is clear, which may happen, for example, if we completely exit the Android application, this task is going to be automatically canceled, because when the view model is destroyed, all this scope is completely canceled. So as I said, the view model is tied to some life cycles. A very common one is actually like a screen or a window. In Android, that's going to be an activity, but if you use multi-platform, that may also mean, for example, just your desktop window. But in the case of Android, for example, this view model scope actually survives events like rotation, resizing, minimization. So you can see that your view model scope actually goes from the moment you call on create. That's where the view model scope comes into being, and then there is like this all star resume, blah 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 blah. And then when you really want to finish it, when you really want to finally destroy it, then the whole composition will ensure that the view model is then clear, which means that every task is going to be canceled, because as part of clearing the view model scope is going to be canceled, which means that every task which was still running, as I was saying, is going to be completely canceled. Now we can actually share a view model between different screens. One way is, for example, to use navigation. So we can have this application in which now the amount of clicks you've done is shown in a different screen than the thing where you actually click. And what I've done here, that's very easily the kind of middle thing in purple is just it's just two buttons. One that says "click me" and will increment the amount of clicks that I've done, and then one to navigate to the other screen. And then in the other screen, we will just have you've clicked this amount of times. So because we are sharing the view model, and this thing is kind of a scope to the whole application, then both things can just, you can go back and forward from one on the other, and this information is going to be saved. Uh, you can also do something different. You can decide that you have a view model for the entire application, but then there is a smaller view model for only one of the screens that you are doing. So it looks a bit like this. There is the app view model that outlives the whole going back and forth. And then when I go to my summary screen, then the summary view model comes into action, is created. And when I go back, because the scope of this view model is tied to the kind of a smaller composable there to root summary, then this thing is going to be clear. And what does it mean? It means that all the memory is freed, all the information is gone, but also every task that I'm creating inside the summary view model are going to be canceled. But anything I create inside of my app view model is still going to be running. And then I can go back to the root clicks, and if I go back to summary, then a new summary view model is going to be created, which is it's not the previous one, it's actually a new one. And then once I go back, it's going to be removed as I was saying. So let's look in this scenario, what are the benefits of this approach of having a CoroutineScope be tied to a view model. Well, as I said, the handling of job is decoupled from the UI. So for example, I can start on one of my screens, I request some data, then I launch a new job, but then I navigate while the new job is still running. So I navigate to a different screen, and then the data comes in. But then the good thing is that I can update my model, and this will actually transform in an updated UI in the actual screen I'm in, because the new job is in this shared view model. When I update it, then the recomposition will actually recompose the screen I am. And then I can also, by the way, go back, and then the information is going to be there. The second thing is that we don't have to worry about leaking jobs, because now my screen can request some data, and then again I will launch a new job. But then this activity is clear for any reason, and automatically this means that the view model scope is going to be canceled, and that means that the new job I launch is going to be canceled. All of this without having to do anything. So the key here is that complex interactions that we had to handle before manually are now just made simple. We don't have to worry about this. Good. Let's see now the backend. To do this, I'm gonna talk about Ktor. Ktor is a framework for creating applications using HTTP, and we have server and client components. But I'm gonna focus here on the server part. So this is like the smallest application you can do. Essentially, this creates well, in this routing block, I can just say different routes, so different places where I'm gonna kind of respond. And then you can see there that this follows this kind of general convention in most HTTP frameworks of having like a way to declare parameters in your route. So if you write hello and then Kotlin conf, then this Kotlin conf becomes the value of the parameter name, and I can just get it by using call.parameters name, and then I can just say respond text to send some response. So the result of this is that I can just call, well, I can just run it, for example, in localhost, and then call hello Kotlin conf, and I will get back hello Kotlin conf. By the way, Ktor is not only for just returning simple kind of HTTP get a request, get a response, be done. You can also create WebSocket applications where the lifecycle is a bit more complicated. You can actually have different incoming messages, and then for each of them you can do something. Here I have a simple example in which for every frame I try to get the text. There is a a distinction in this protocol about binary and text frame, but it's not so important here. I'm going to get it, and then I will go back. I will give back hello and this name. So if you use, for example, the built-in HTTP client in IntelliJ IDEA, which supports WebSocket, you can start doing this. And there you see I wrote Kotlin conf, I get back hello Kotlin conf. I write everybody, I get back hello everybody. This is why I'm telling this is because I actually want to show you that these different things go into different scopes. So let's look here at kind of a combination of these two simple applications. I have my application, that's the whole scope of it, and inside of it I'm having two routes. I have the get one, and then the WebSocket one, and I'm again making explicit what the receiver type is. So inside my application block, this corresponds to application. Inside my get, this corresponds to something called pipeline context. Doesn't matter too much. And in WebSocket, I have a WebSocket server session. What is interesting about this is that, surprise, surprise, all of this extend CoroutineScope, which means that the same ideas I've been talking in the compose part actually move into this other realm of backend application using Ktor. So let's look at a couple of examples to actually see how this is important. So I'm doing here a bit of complex thing. Let me briefly explain this. So what I have here is a handler for my root example, and then I'm launching something, and because I'm not using an explicit receiver, this will go to the closest one, which is, it means this is the pipeline context, the context of this particular request. And then what I'm doing is I'm gonna launch something, and then I will print the request scope start. I'm gonna delay for 2 seconds. That, let's do the usual thing, which we wait instead of doing actual work to kind of simulate we are doing something, and then we end. And then I'm using this special function from the coroutine library, which allow me to actually hook to the completion of this coroutine and see, of this task, and see why this was completed. And then I'm going to do something similar, but I'm going to launch my task in a different CoroutineScope. In this case, in the application CoroutineScope, which is going to be defined outside. And to do this, I'm going to use this add app that actually goes back to the name I gave there to the function. So this means this corresponding to the app function, which is going to be application, as you can see in this diagram. And then I'm just going to have the usual thing where I respond with something, and I will print things. So the idea here is that kind of the two operations, two things are going to be launched concurrently, and they are actually going to be concurrently with the handling of the request. So let's see what happens there. Good. So what we see there is that the request scope start, the handler start, the application scope starts. This can actually be almost in any order because, well, we don't know where these different things are actually going to be done, but the three things start. Then we will respond done. So that means we are actually sending done through the wire. And then, well, we are going to actually wait for 2 seconds. And 2 seconds later, we're going to see application scope and request scope end. So both will end. We don't know the order, but both will end. And then we will see that that we will invoke this onCompletion thing and have the request scope cause null. And this null means that we are actually waiting on the usual way. So this is not canceled. This is just ending in the normal fashion with a successful completion. So what you can see there is that actually, even though we might be thinking, oh, I'm finished, after handler end, we should just stop and don't wait for anything else. We can see that we have actually waited until the request scope have printed end to wait. And that's because, remember, every scope always wait for all the children to finish. Even though this is not an async and we are not awaiting it, we always wait for every job we've launched unless we do something explicit to cancel it. And how we can do it is by actually calling canceller. So if I call cancel in a CoroutineScope, that means I want to cancel, well, the CoroutineScope where I'm calling this thing. So in this case, what happens is that we see that because, well, the handler starts, done, and end is going to be very fast, less than 2 seconds. Actually, the request to scope end is not going to be printed because we are canceling this. And then we can also see that the request to scope has been completed with a cause. And if you read what's there, you will see something like cancellation action. So this has been canceled. So this is a way in which we can actually, at this point, cancel everything we've been doing in this CoroutineScope and just, well, we can see it there. However, the other launch, the blue launch, was done on the application scope. And the application scope is bigger than the one with cancel. So we see that after 2 seconds, actually the application scope end name is going to be printed there. So the job started in the application scope is going to be completed because it's not part of the scope we have canceled. And why this is interesting is because being aware of this different scope allows us to build better Ktor applications. We can respond faster to requests. For example, we can update the database in the request scope, but maybe the cache can be done separately on the application scope. We don't have the whole request doesn't have to wait to do this. Sometimes it's also interesting because sometimes it seems that you have actually given all the information through the wire, but still the request is somehow going on. And in many cases, this is because the request is still alive, because even though the information has been produced, there is some job which has been launched, which is still running. And the counterside of this is that you can actually easily cancel all jobs if one step facing your request. Imagine that at this point you decide, oh, I cannot continue, right? I need to give some kind of 404. Well, just give it, and then you cancel the whole request, and then you are completely sure that every async, every launch you've done inside this block is going to be automatically canceled. So again, something which usually would be a bit complicated is now become very simple because of this child-parent relationship. Good. So we've talked about Ktor, we've talked about Compose, we've talked about CoroutineScope, and this adds structure to concurrency, right? And this structure means it knows about join, it knows about cancellation, it knows about exception propagation. But the idea of a scope is useful for other abstraction. And to do so, I'm going to show you very briefly 2 examples coming from the Arrow library. One is resource management. And how is the idea of a scope related to resources? Well, in this case, what we want to do is whenever we start some kind of resource block, we may want to acquire some resources. And we know that by the end of this block, we want to dispose of those. And here is the example. Here, the resources scope is the parent scope. And then we have different ways to create child resource management, child scopes, where we can, for example, create a Divi connection. We do this with install, or if your thing actually implements the auto-closable interface, you can just call auto-closable, for example, here in the HTTP client. And then you know that by the end of this resource scope, all of this is going to be automatically disposed without having to do anything, right? So use it. No need to nest, try finally, no need to nest. Use all of this, again, because we have this parent-child relationship here. Another place where this idea of a scope comes into play is in distributed transaction. And the idea here is how we can ensure that we have some transactional behavior when multiple services are involved, right? When we have 2 different services that actually don't talk to each other. We somehow need to orchestrate all of this. And each of these services, by the way, may succeed or fail independently, right? But we know that this orchestration should ensure that by the end, we always end in a consistent state. It cannot be the case that whatever we did in one of the services is somehow not roll back, and then we have some kind of inconsistent state, some kind of actually garbage in our server. So sagas are one of the patterns to handle this scenario. And the idea here is that for each action, we are gonna tie a compensation action that undoes this. So here I have an action which is incrementing, and then a compensation action which is going to be decrementing, right? And then if there is a problem, if there's an exception within this saga, instead of doing, let's say, what a CoroutineScope would do, right? A CoroutineScope, if there is an exception, goes to the children and says, well, rest of the children, please cancel. In this case, we're going to do something different. There is an exception. This saga scope ensures that it goes to the children and says, please run the compensation actions actually in reverse order, so we go back to a consistent state. So we can see that it's the same idea, right? Is that we have the parent and then children, but the difference here is what happens when we have an exception. In one case, we just cancel. In the other case, we run compensation actions. And now it's maybe the moment in this last couple of minutes to talk about this idea of dispatching, right? And I've mentioned at the beginning of the talk, I like to think of a scope as a conceptual tool, as a logical way to express how the task work in my concurrent operation. But then we have a coroutine scheduler, which is free to run those actions whatever it sees fit, right? The only thing is, please do whatever I've been telling you to do, right? Propagate, cancel in the way that the structured concurrency rules says. But other than that, just scheduler, do whatever you think. You try to optimize for whatever you want. And the way we can actually influence how the scheduler runs is by using so-called coroutine dispatchers. So what we often see that we don't think too much about it. We just inherit the dispatcher from the parent scope. But for example, if at some point you are going to do some IO intensive tasks, it's interesting to look at dispatchers.io because, well, it has a different set of defaults which are better geared towards doing IO intensive work. But again, this is, at the logical level, this is not so important, right? If we have a perfect dispatcher which knows about this, we would need to do this, but sometimes we need to give hints in order for the scheduler to know how to better schedule our task. Good, so that's it. The conclusion here is that scopes provide a way to structure the application. In this talk, I've mostly talked about CoroutineScope, which take care of correct joining cancellation, in general of structured concurrency, but I've shown how other scopes, resource scopes, saga scopes, provide some other additional behavior. And in a big application, and this could well be a composed application with view models, Ktor server where we have different routes, we have different smaller and larger scopes living at the same time, living alongside. So if you want to remember like your catchphrase from this talk, remember, think where you launch. Thank you.